This talk is polynomial root by optimization, which is a little bit unusual. I want to dedicate this talk to Valentin Albillo for his contribution to one of the algorithms that I did, and I'll explain this a little bit later on in the talk. Now, I have two general approaches. The first one is the quasi-Lin-Bairstow method, and then the second one is the combined Newton-Vieta method. That's what I'm calling it. And my target is the set of real and imaginary roots in real coefficient polynomials. And equation 1 shows you a typical general one. To make things a little bit easier, we divide all the coefficients by a sub n and get to simplify the polynomial a little bit, as shown in equation 1b. Now, the legacy Lin-Bairstow method works by systematically and iteratively extracting quadratic polynomials whose roots are also the roots of p of x. And we have in equation 2, p of x is q of x, the quadratic polynomial. B of x, that's the deflated polynomial that we will obtain. And then R of x is a linear remainder, it's a straight line. And you have q of x is x squared plus q sub 1 x plus q sub 0. That's the quadratic polynomial we're extracting. R of x is the linear remainder. And it's r sub 1 x plus r sub 0. And when q of x is an exact, it has the exact roots, real or complex, of p of x, the coefficients of r of x are both 0, because there's no remainder. Now keep in mind that the original p of x, the polynomial, is repeatedly deflated by an order of 2 every time. Now the legacy Lin-Bairstow is one of my favorite, and it can be implemented on a wide range of variety of hardware and programming language, because it doesn't really need support of complex math. So you can implement it on calculators like the 41, 42. You need a little bit of memory. Now each quadratic polynomial has either 2 real roots or a pair of conjugate roots where the imaginary parts have opposite signs. And we deflate a p of x and repeat this process until all the real and complex roots are extracted. That's if the order is even. If it's odd, then you will have a remaining simple linear equation, and getting the root of that is easy as pie. Now, my new approach is the quasi-Lin-Bairstow method. I'm using the same approach, but I'm extracting q of x through optimization. And we have q of x defined here. And basically I'm saying I tweak q1 and q sub 0 until the sum of the remainders, r sub 1 squared plus r sub 0 squared, is 0. If that's the case, then I have the roots for the quadratic that I want. And I use MATLAB to handle the optimization. The latest version of MATLAB has the particle swarm function. That's a robust implementation of an evolutionary algorithm for the particle swarm optimization. If this sounds a little familiar from your memory, is because I think maybe 2 years ago in Nashville, I presented an implementation for that algorithm on the HP prime. Now, the BSO has been found to work with a wide variety of algorithms, but we should never forget the no free lunch principle that states that no single algorithm will solve all optimization problems. So we shouldn't, we should, be guardedly optimistic about that. Now, we can use other classical optimization methods or other different evolutionary, and there's plenty of them. I study and play with them all the time. There's quite the number of evolutionary optimization programs that are solid and perform very well. Now, the problem is that many cases the optimization algorithms fail to correct to return the correct roots. There is an infinite number of polynomials, and like people, not all of them are, some are easy to deal with, some are very difficult. And, you know, so some legacy algorithms will do well with some polynomials, will have a hard time giving you the correct answer in other cases. I coded a function here, SLB, that's based on the quasi-Lin-Bairstow method. And the parameters are polycoefs that is the array of polynomial coefficients. It identifies what we're dealing with. The toler is the tolerance we're using. And max iter is the maximum number of iterations that we are using with the particle swarm function. And max retry is the max number of attempts of using or reusing particle swarm. There's a way to check if the machine, if the answer failed, because the algorithm uses random numbers. It initializes the potential solution with random numbers, so you may get a hiccup. I'm using max iter from extra caution. Normally, the first try, it'll get it right. The output parameters, we have xroot. It's a two-column matrix. The first column is the real components. The second column is the imaginary. And if the root is real, then the imaginary part is 0. N root is the number of roots you get. And here's an example. I have a polynomial, I think of the order 6. So it's x to the 6th power minus 2, x to the 5th, and so on. And I run it. I give it a tolerance of 10 to the minus 10, that's kind of a little bit strict, 1,000 iterations and 50 times retries. And the blue text is what the function outputs, including the correct answers. I have 2 real roots, and then a pair of conjugate roots, and another one here, and you can see that they're different in the minus sign. And the number of roots is 6. It's a 6th order polynomial. The second approach, I used the Vieta formula. It was mentioned in the HP Museum in one case, and I was looking at, Now, the Vieta formulas describe the relationship between the polynomial coefficients and the roots. And for a polynomial of order n, you have n plus 1 equations. The first equation and the last equation are the easiest. The first one is just the summation of the roots as related to the highest 2 coefficients, and the last one is just the product. In between, it becomes very, very messy and very difficult to figure out. And like I said, here I have n plus 1 equations. Now, the basic approach I propose is to optimize the roots starting with guesses, okay, until all the Vieta formulas are fulfilled, obeyed. And so I have basically equation 3 shows me that the left-hand side minus the right-hand side squared, and I add them. And basically, I need to optimize this. I approached the problem by challenging the people at the HP Museum website, if you can get me something like that. And sure enough, within a very short period, Valentin Albillo, in his brilliant, the man just blew me away. I was floored. He provided me with an HP71B basic using a complex math. And he was able to calculate these summations, the function in equation 3. The thing is, his solution was so elegant, I went over it again and again, and I looked at it with disbelief. It was so simple, because I was contemplating if I solved it myself, the thing to be so complex with extensive bookkeeping, and he had it in simplicity. I looked for other solutions on the internet. I found one in C++ with some minor errors. Other than that, nothing. People would talk about the Vieta formulas, but nobody dared to code it. It's like, we're not going to go there, you know. So So Valentin did a fantastic job, and he gave me the tool that I needed. Without his help, there would be no method. So I approached the problem, optimization, the Vieta formulas, in a very general term, kind of casual, cavalier, asking for trouble. So I took into account that each root is basically complex. I mean, that's my worst assumption. And if it's a real root, then it'll have an imaginary part. Okay. And this meant that a polynomial of order n will have, I have to optimize two n variables. I'm asking for trouble right there. And the result is a big jumbo fiasco. It's like traveling with parachute luggage. You're just asking for trouble. And why? Because I gave the optimization system a high degree of freedom, and I made the assumption that it was smarter than it really was. That the optimization formula was too general. So back to the drawing board, second attempt. This time I said, what I need to do is I need first to extract the real roots. And to that I can use Newton, okay? Newton's method. Now, working with MATLAB, you have, and I will mention that, MATLAB supports a seamless shift between real math and complex math, something that we would have dreamed of 30, 40 years ago about machines doing that, okay? And so I had to force MATLAB to handle stuff in real mode. I did not want it to encroach the complex area. So I used MATLAB to extract the real roots, deflate my original polynomial, and I end up with a deflated polynomial that I give to use the Vieta formulas to handle, there will be all pairs of conjugate roots. Now, there's Descartes' rule of signs. It kind of gives you an estimate of the maximum number of, real and complex root, but it's not an exact, so it wasn't a real help. So I had to kind of wing it. So I said, okay, I'm going to use again MATLAB, and I'm going to optimize the variables. For example, the variables x1 and x2 will form complex conjugate x of 1 plus I x of 2. That makes it a complex number, and x of 1 minus x of 2. And to be used in the Vieta formulas. Same thing if we have x3 and x4, I get two complex variables. This reduced the optimized variables from 2n down to n. So first of all, I brought the number of optimized variables to n. That helped. And then I coded the optimization function to keep track of the fact that I'm using complex conjugate roots, and that helped. That made a big difference in the outcome. So I used Newton to remove all the real roots for the p of x, and then I optimized the sum of the squares of the functions in the Vieta formula on the deflated polynomial that has shed all of its real roots, now containing only pairs of complex conjugate roots. That made it easier. And then, of course, every time I extract a pair of complex conjugate roots, I repeat the process until I'm out of roots. And I wrote a function called Newton polyroots x. It's similar to the other function. The parameters are similar, except here I have max iter. I use this to tell Newton's method that you basically ran out of real roots to extract. If you do, say, 100 times and you find nothing, means we're done here, okay? We move to the second phase. Max iter optimum is the maximum number of optimization that I use with the particle swarm function call. So, and the output is pretty much the same. And it's the same problem here I have using the sixth order polynomial with the Newton poly, and I have my tolerance 10 to the minus 10. I give Newton 100 iterations. After that, if you don't find anything, get out, you're done. And then 1,000 for the maximum iteration for the particle swarms. I don't need to do maximum retry because I've preconditioned the polynomial for stage 2 in a very well manner. And here's the example. As you can see, the first two roots are the real roots that Newton has obtained, and then the second phase gives me the two sets of complex conjugate roots, and I get, so it's basically the same answer. Now the conclusion, the quasi-Limberstow algorithm depends on the optimization methods. Some work better than others. Now the Newton-Vieta algorithm is very robust, and I've tried it with different polynomials and it can handle them. And the reason is there's more discipline at work. I'm not just sort of throwing variables willy-nilly and hoping that the algorithm return. I have a little bit organized thing. Now it's interesting, when you program in MATLAB and its free counterpart Octave, of course, it handles the shifting, seamless shifting between complex and real math. And actually you can write, after I've done this, I went like, I can write a Newton's method in MATLAB that will obtain the real and complex roots for real coefficient and complex coefficient polynomials. So again, given the right tool, something like MATLAB, you can accomplish a lot, something that we would have dreamt about way back when. And that's all. Thank you very much.